Hello, my name is Anton Pirhonen and I study computer science at Aalto University. In this video, I will give a presentation about explainable linear regression. I will also show two experiments that I've conducted with the algorithm. Let's start by looking at the problem and the data. My goal is to predict the maximum daytime temperature in Kaisaniemi, Helsinki. Thus, the label is the maximum daytime temperature in Kaisaniemi. I have 5 features which were the maximum daytime temperatures from nearby locations from the same day. Additionally, each data point includes a user signal which is used with the explainability part of the algorithm. Training data consisted of 365 data points and validation data of 366 data points. The data was obtained from the Finnish Meteorological Institute. Here's a graphical image of the problem. So the locations with red arrows mark the locations of the features. And this green dot is the label location. Alright, the user signal is an addition to the data point, and it characterizes the data point from the perspective of a user. In this context, of this experiment, the user signal could be, for example, the user's prediction about the following day's maximum daytime temperature. So here we see the 5 features, the label and the user signal that make up a data point. Next, I'll talk you about model and loss. So I'm using explainable linear regression, which is from a paper by Zhang et al. Here, the user signal is utilized with conditional entropy to quantify the subjective explainability. And the subjective explainability is applied as a regularization term to standard linear regression. For more details about the explainability, I suggest you look at the paper by Zhang et al. Now, let's look at the explainable linear regression algorithm. There are 2 inputs. Other is the dataset, and other is an explainability parameter, which is some non-negative real number. Next, we want to solve this following minimization problem. So we want to find weights that minimize this function. Then we will output the weights, which is also our hypothesis. Okay, let's look more closely at the minimization. So the function that we want to minimize consists of 2 parts. Other is the empirical risk and subjective explainability. And we want to find weights that minimize this sum. The empirical risk is measured with squared error loss, and the subjective explainability is measured as the squared error between the predicted label and the scaled user signal U. Additionally, there is the explainability parameter, which is used to control the emphasis on the subjective explainability. With big lambdas, the algorithm will focus more on the subjective explainability, and with small lambdas more on the minimizing the empirical risk. When lambda is 0, the algorithm is essentially just the regular linear regression algorithm. Next, let's go to the experiments. I have implemented the algorithm using SciPy, and in this experiment I simulated the user signal by using the maximum daytime temperature from Kaisaniemi from the previous day. Okay, here we can see the user signal from Kaisaniemi and compared to the label. On the y-axis is the temperature, on the x-axis the day, and this was the maximum daytime temperature. So we can see that the label and the user signal are very similar to each other. This is essentially a very good user signal. The value of the user signal is shifted 1 day right and it's otherwise same as the label. So with this user signal, the training error looks like this. Here on the y-axis we have mean squared training error, and on the x-axis we have the explainability parameter lambda. I have used a logarithmic scale to visualize a broader range of lambdas. So we can see that training error increases as we increase the explainability parameter lambda. Next is the validation error, and it's also measured as mean squared error. Here we can see a different story. So once we start increasing the explainability parameter, the validation error actually decreases. At some point it reaches minimum and then starts to increase. What this means that the explainable linear regression using an accurate user signal can have a smaller validation error compared to the standard linear regression. For the next experiment, I wanted to find out what happens with a less accurate user signal. Also, what happens when we increase the explainability even more, and how do the regression weights W and the user signal scalar alpha perform. The next experiment is conducted with a less accurate user signal from Jyväskylä, which is located 235 kilometers north of Kaisaniemi, Helsinki. And I also increased the range of lambda. Here we can see the same user signal plot, but with different user signal this time. We can see that there is more difference between the user signal and the label. Thus, this user signal is essentially a worse user signal than the one I used before. Here is the training error, and this time we can see that it increases, but different from last time, the error actually starts to plateau. It does not seem to be increasing forever. The validation error also shows a similar shape as the training error. Here we cannot actually see whether this using the user signal improves the model. So on the next slide I have zoomed to this part. And we can see that there is a slight decrease in validation error, but it quite quickly starts to increase. So the user signal is not able to improve the model very much. Here are the regression weights, and we can see that there's one weight that is increased and then decreased. These three weights quite quickly near zero, and this one weight that decreases and then also starts to near zero. Importantly, we can notice that all the weights are quite close to zero when we have a lot of explainability. Here is also the user signal scalar alpha, and we can see that with low explainability, the alpha is quite close to 1. And once we start adding explainability, the user signal starts to be scaled towards 0. So here the user signal is used as it is, whereas here it is almost 0. Yep, here's a recap of the observations. So the user signal only improved the validation error a little bit. The training and validation errors started to plateau with large values of lambda. And the regression weights, the user signal scalar alpha, approach 0 with large values of lambda. And why does this happen? This is because when the subjective explainability parameter lambda is set very high, then the loss from the subjective explainability part is heavily penalized. And this can be minimized by setting the weights and the alpha to 0. So then the term inside will be 0 and there will be no loss from the subjective explainability. But this also leads to the model constantly predicting 0 because it's essentially a flat model. Here is a visualization of that. So here, when we have some small lambda, we have the predicted label or the model here, depicted with black. Then we have the labels and the user signals. And we can see that the model is making a compromise between the user signal and the label. But here, when lambda is very large, we can see that the user signal and the model, or the weights, are scaled very close to the 0. And that is because the errors from between the model and the user signal are then also very small. And thus also the error from the square error loss is bigger. So, to conclude, we noted in this experiment that using an accurate user signal with explainable linear regression can improve the validation error compared to standard linear regression. We also noticed that the asymptotic behavior of the model with respect to the explainability parameter lambda approaches a linear model with 0 weights. And here a topic for further research is studying and experimenting with alternative definitions of subjective explainability. Here is the paper that I was referring to. If you're interested, please check it out. Alright, thank you for watching. Have a nice day.